Executing the K means clustering algorithm requires you as a data scientist to make some design choices. What are these design choices? There exist several clustering algorithms which allow you to group data based on their characteristics. One of the most popular and the one that's most commonly used is the K means clustering algorithm. Let's get a big picture understanding of how this works. Let's say these are the points that you have in an n dimensional space. We are expressing it in two dimensions because that's what is easy for us to do on screen here. But imagine that each of these points have n attributes, and all of these attributes are expressed in the form of numbers. These are points in an n dimensional hypercube. Our objective is to find k clusters or groups within this data so that points which belong to the same group are similar to each other and points which are in different groups are different from each other. Remember that the objective of clustering is to maximize intra-cluster similarity and to minimize inter-cluster similarity. To kickstart the algorithm, we'll start off by initializing k centroids. These k points will be the centers of the logical groups that we're going to form, the centers of our clusters. So these k centroids will be initialized kind of at random when you to kickstart the algorithm. Once we have the k centroids initialized, we'll iterate through every point that exists in n-dimensional space and assign the point to the nearest cluster, that is, to the centroid that is the closest to that point. We'll use some kind of distance measure to calculate how far away a particular point is from one of the centroids, and we'll choose the centroid that is the closest to that point so that we have a number of points which belong to the pink centroid, to the purple centroid, to the green, as well as to the blue centroid. Because we have initialized k different centroids and we've associated points with each of these centroids, what we have now is some approximation of points in k clusters. Once we have these clusters set up, go ahead and recalculate the mean for each cluster. The average for each cluster now depends on the points that belong to that cluster, and this mean is now the new centroid of that cluster. Once you have the new centroids, you'll repeat the step that you performed previously. Iterate through all the points and calculate the distance from the centroids and assign the points to those centers to which they are closest to. You'll find that some of the points may have shifted. They are now closer to some other centroid than they were previously. Go ahead and reassign these points to the new clusters and continue this till finally all your clusters converge. Iterate till the points are in their final clusters and you find that points no longer move. You might find that points move around a lot initially and then finally points remain where they are. This is convergence. Once your algorithm has converged, your entire cluster can be represented using that single point. This cluster center is often called the reference vector. One of the most common ways to calculate the cluster center is by finding the average of all the points which belong to a certain cluster. This is the centroid of that cluster, which is why we used the term centroid earlier. Reference vector is a more general term. Centroid refers to those cluster centers that are calculated in a particular way. Here is the basic algorithm that you used in K-means clustering in order to find clusters in the data. We start off at the very first step where we initialize K-centroids. We call them centroids, but the more general term is reference vectors. Important thing to remember, people often call them centroids, but they are centroids only if they're calculated in a particular way by finding the average of all the points in a cluster. We have to start somewhere, so we have some initial solution. Let's say we want to divide our data into k groups. We pick k cluster centers, and there are algorithms which exist which help you pick well. You have to examine your data properly as well. Then for each data point, you'll assign that point to the nearest cluster. And this is the step that you perform over and over again. This is the iterative step. We'll iterate until convergence. At the end of every iteration, we have a new set of data points in each cluster. They may have changed much, which will be true at the beginning. They will not change when you're closer to convergence. Closer to convergence, fewer and fewer of these points will move from one cluster to another. Now that we have all the points in a cluster, we update the reference vector or the centroid of each cluster. After every iteration, you'll check to see whether there are any points left that move from one cluster to another. If the centroids have converged, which is when no points are reassigned, then yes, we can stop, we are done. If points still move around between clusters, that means our algorithm hasn't converged, we continue iterating. Every step in this algorithm requires some decision that we need to make or some tuning that we have to perform. And at the very first step, there are a number of hyperparameters that we have to determine and that we can tune. The two main hyperparameters in K-means clustering is the number of clusters that we want to group the data into and the initial value of the centroids. At the next step, we have some additional design choices which will affect how our clusters are set up and how well our algorithm performs. The very first design choice is how do we measure the distance between the point and the reference vector of the cluster. For a point in n-dimensional space, you know that there are several distance measures that we can use. The one that is the most commonly used is Euclidean distance. Next comes the step where we want to update the coordinates of the cluster centers. Now, the reason that we often call them centroids because the method by which we update the points is often just by calculating the simple average of all the points. The simple average of all the points gives us the centroid, which is why the reference vector, which represents a cluster, is often called the centroid. This is once again a design choice, though. Now, our objective in finding the reference vectors which represent clusters and in grouping the data is to minimize something called the total reconstruction error, because it is this reconstruction error which finds the best fit for our k-means clustering algorithm. The lower the total reconstruction error, the better the fit of the logical groupings or clusters in our data. Let's define what this total reconstruction error is. Let's say these are the points in our n-dimensional space. These are the cluster centers represented by stars, and we're using Euclidean distance to measure the distance between a point and the cluster center. If the Euclidean distance is represented by d, then the square of the Euclidean distance of each point from the nearest reference vector is d square. Calculate the Euclidean distance from all cluster centers to all points which belong to that particular cluster and square their values. So find the square of the Euclidean distance for all points with all cluster centers and sum over all points and reference vectors. This sum is the total reconstruction error. The total reconstruction error is equal to the sum of the squares of the Euclidean distance between all points which belong to a particular cluster and their reference vectors. We've spoken about hyperparameters before and how tuning them helps us generate better machine learning models for our problem statement. Hyperparameters are basically model configuration properties that define a model and they remain constant during the training process. You can tweak the hyperparameters and generate different models and choose the one that works best for you. In order to understand hyperparameters, let's consider three important terms associated with any machine learning model and its training process. The first of these is the model inputs, then come the model parameters, and then the model hyperparameters. Model inputs are what we use to train our machine learning model. These are the input data points. In the case of supervised learning algorithms, these will be data points which have associated labels. This will be a labeled corpus. In the case of unsupervised learning, this will be an unlabeled corpus. In any case, these data points are used to train our model parameters. And this brings us to the model parameters. The model parameters are the values that are tweaked and updated during the machine learning training process. And these model parameters help us make predictions. In the case of neural networks, they are weights and biases. In the case of k-means clustering, the model parameters are the reference vectors or the centroids of each cluster. And then we have the model hyperparameters. These are the parameters that we can tweak and set before we start the training process for our machine learning algorithm. But once training has started, hyperparameters remain constant. Hyperparameters are design choices that we make when we set up a machine learning model. The design choices for K means clustering are the number of clusters or number of groups we want to divide the data into, the initial values for the centroids of these clusters, and the distance measure that we are going to use to figure out whether a point belongs in a cluster or not. The choice of these hyperparameters when you perform k-means clustering might depend on a variety of factors. The problem statement that you're looking to solve, the kind of data that you have available, how efficient you want your computation to be, and so on. Let's start off by looking at the number of clusters. The most important hyperparameter that you need to specify in k-means clustering is basically k, the number of clusters or groups you want to divide your data into. Now, sometimes the value of k may be obvious. Let's say you're using k means clustering as a way of grouping together MNIST handwritten digits. This is one of the demos that we'll do. You know that the number of digits are 10, so the number of clusters should also be 10. This is kind of an obvious thing. If your problem statement is handwritten digit recognition, it makes no sense to group your data into 5 clusters when there are 10 digits. But sometimes the number of clusters may not be that obvious. You don't know what logical groups exist in the data. In such a situation, the only way to figure out the number of clusters which seems right is by performing some kind of tuning. You'll plot the average reconstruction error against the value of k by choosing different values of k and identify the elbow. Let's see what this means. Let's say you have a 2D axis, the x and the y axis. You plot k along the x axis, and along the y axis, you have the average distance from every point to the centroid of the cluster to which they belong. We'll start off with k is equal to 1, which is you don't divide the data into clusters at all, and find the average distance of every point from the centroid of that cluster. You'll get some value. Now, let's say you move to 2, 3, 4, 5 clusters. At every step, plot the average distance of every point from the center of the cluster to which that point belongs. And you'll probably end up with a line which looks like what you see on screen. There will be some value for number of clusters where you'll find that the average reconstruction error will suddenly drop. This is the elbow, and you'll typically choose your number of clusters at this elbow. Here, k should be equal to 3. The initial values of the reference vectors that we choose is also an important hyperparameter. That's because it's been noticed that the final reference vector values are very sensitive to what values we initially assigned. Random initialization may not work best, though typically that's what people usually do when they're prototyping data. Some analysis of the data might help in order to figure out the right initialization values. One suggestion for figuring out the right initial values for your data is by performing PCA or principal components analysis. Once you have the principal components, you'll normalize them and divide their range into k parts, where k is the number of clusters. Take the average of each of these ranges, and these averages can be your initial values. Another design choice that you need to make when you perform k-means clustering is to figure out what distance measure you're going to use to calculate the distance between a point and the reference vector. There are several choices out there. The most popular of these is Euclidean distance. Remember, the centroid that you calculate for a cluster may not be an actual point in your data set. You could also choose other distance measures such as Mahalanobis distance, which is typically used to calculate the distance between a point P and a distribution D, or cosine distance. Find the cosine of the angle between the point and the centroid. There are three important hyperparameters or design choices that you can make when you run k-means clustering. The first is the number of clusters. How many logical groups do you want to divide this data into? Sometimes the answer might be obvious, like in the case of digit classification. At other times, you might have to plot the value of k against the average reconstruction error of your algorithm. You'll choose that value of k at the elbow where the average reconstruction error falls. Other hyperparameters are how you initialize the cluster centers. This can be done at random or by examining the underlying data and performing PCA on it. The third important hyperparameter is the distance measure that you use to measure the distance between your cluster center and the points which belong to that cluster.